All right, so now let's go ahead and see how we're going to do this computation. It is actually very clear that the gap itself, it doesn't actually implement the needed interresonator coupling. But the gap with a transmission line section to the left and to the right, it does. And actually, it turns out that this length that is needed is basically going to be negative. In fact, you may go back in your notes and recall that we did discuss some implementations of J sections, of coupling sections, where essentially we needed negative transmission line lengths. That's exactly the case here. We need the negative transmission line length to the left and to the right of the gap. Of course, there is no physical way to realize a negative transmission line, but remember that the real transmission line to the left and to the right is going to include a positive length. So all we really have to do at the end of the day is subtract this needed length from the physical length that we have from the resonator anyways. So in order to basically do the calculation, the ABCD matrix becomes very handy here, because the ABCD matrix of a cascade of 3 devices, so here's the first device, here's the gap, and here's the third device, can be very easily computed. We already know, I've given you in the beginning of this lecture series the ABCD matrix for the gap. We also know the ABCD matrix of a transmission line, so you just multiply the 3 and you get the ABCD matrix of the whole cascade. Now, that ABCD matrix must be equal to the ABCD matrix of the J inverter that we also know. So if you do all of this, and I'm sparing you quite a bit of algebra here, you will basically find out that the needed lengths are linked to the angle phi that I'm basically writing here. And it's actually more convenient to express this with regards to phi1 and phi2, where phi1 and phi2 are each related to the BA, the susceptance that we looked at earlier on for the gap. If you remember, the equivalent model for the gap is this one here, where we have BB here, BA to the left and to the right. So that's the BA that you see up there. And then phi2, the angle here, is also related to this BA and this BB. So one more step is actually required to make that link more explicit. And so we can basically take the J, which is the inverters that we have already computed. And again, after a little bit of algebra, we can actually directly link them to those angles phi1 and phi2. So the process, in other words, now is the following. I have found the equations for calculating J. And once I found the equations to calculate J, I can calculate the angles phi1 and phi2. And once I know those angles, I can calculate BA and BB. And then once I know those, I can calculate the real gap, because this BA and BB is related to the real gap, and I've given you the equation for this before. The problem is that the equations are slightly messy here, so you can't really make this solution explicit. So to kind of proceed to the next step and show you a little bit more explicitly how this works, I'm going to make some approximations here. So it turns out from a physical perspective that as long as the gap is much, much smaller than the height of the package, remember that this is the height here, this is the height of the package for this suspended microstrip line. So as long as my spacing is much, much less than this h, which is true, by the way, in almost all physical realizations, the susceptance BA is actually much less than the susceptance BB. So if you actually make this approximation, you can have a non-iterative solution. And it turns out then that phi2 is explicitly linked to only BB, and then J is only linked to phi2. So now I have an explicit equation that I can actually use to find phi2 from J. And once I know that, find BB from phi2. So that's exactly really how the process goes. These are the equations, again, I'm using for linking this. And eventually, I'm going to find the gap S, which will be related to BB. And once I know my gap S, I can also find BA, which again is going to be a much smaller number than BB, because the equations are there for BA, as I've given you that before.